operational amplifiers. So
Yes.
Operational amplifiers. Typically, people start with examples like inverting amplifiers. Well, actually, I myself start by giving example of inverting amplifier and then develop. But I think today I want to start with a different approach. I want to somehow give some sort of deeper understanding of how operational amplifiers work. And I would start from the concept of feedback system. I think you're familiar with that if you studied automatic controls.
No, I didn't take the subject, but I'm sort of vaguely familiar, let's say.
In fact, it's the base. Everybody has some experience with the feedback systems.
There's a P, there's an I, there's a D.
Okay, yeah, that is PID controllers. But even before arriving to the PID controllers, in the very basic system, let's say the typical example they give is always about the heating system of a house, right? That you have a heating system, you set a temperature, then you measure, the thermostat measures the temperature, and it keeps warming until you arrive. So I don't like very much that example because it has some delay.
Yeah.
And so it doesn't mean that you warm up, you start the heating system and immediately it gets to a temperature.
Yeah.
And typically it's on-off.
Yeah, it's not like light where you would see the
exactly. Much better example would be like give power to the light bulb and measure, I don't know, with a photodiode how much light you get and then adjust. But let's imagine that we have
or an RPM of a fan.
Or that's also, but also that there is some. Never mind. Let's assume that we have, I don't know, an electric oven.
Yes.
That you put some electric power in and it warms up. And let's assume that it's ideal. So
no losses.
No losses. Well, all the electric power is it, but especially there is no delay. Okay. So it's just you put some power, and instantaneously it goes to the steady state temperature.
Okay.
So we have this oven, and let's say that I don't know. You want to bake a sponge cake. You know what's the temperature for a sponge cake?
I'm going to guess 180.
Excellent.
Ready?
Yes. Yes. Typical temperature for a sponge cake, 180. That is 30-40 minutes. After that. So you want to arrive to a temperature of 180 degrees. Do you really guess it?
Yeah.
180 degrees of Celsius, okay? And so what do? You have your oven. You give, I don't know, 100 watts. And say, okay, I'll power it 100 watts. Then you get some temperature, okay? You measure, I don't know, 50 degrees. Okay? So what you do is to say, okay, fine. I want 180 degrees. Okay? I measure 50. Okay. I calculate, okay, I want 180 degrees. So far, I have 50. So the difference is positive. So it's 130 degrees. So it means that I have to increase the power. Okay? So instead of giving 100 watts, 100 watts, I have to give 200 watts. Instantaneously, the power will go to, I don't know, 80 degrees, okay? 80 degrees, I bring it back, and I say, okay, I want 180. I have 80 degrees. It means that I have here a difference of 100 degrees. It means that 200 watts is not enough yet. So I will increase it to 300 watts, okay? And then the temperature becomes, I don't know, 120 degrees. I'm just giving random numbers.
Yeah, I got you.
120, I check and say, okay, I want 180. I have 120, I get 60 degrees of difference. It means, fine, I'm going in the right direction, but still I need extra power. So I give 400 watts, and I get 180 degrees of Celsius. Then I bring it back. I have 180, which is what I want. 180, which is what I achieved. The difference?
0.
It's 0. And therefore, say, okay, fine. I don't move anymore. It means that the power is correct. And it stays there. Okay? So the system checks at the input what is the difference between what I want and what I achieved. If the difference is positive, it will increase because it means that it's not enough, the power that you give to the oven. On the contrary, if I add, for instance, here 200 degrees, say, wait, too much. So here I would have 200 degrees. So the difference now would be minus 20, which means, hey, man, you're warming up too much. So you have to decrease the power, okay? Because the temperature you have in the oven is more than what you want. So it's automatic. So here, it checks which is the difference between what you have, what you want, and what you have, and automatically increases or decreases the power to the oven in order to achieve the temperature. Okay? So this is the simplest way an automatic system. And it's called feedback because it feeds back, okay? And
what you created is fed back into what you'll give.
What you want to create, and then you give to the system.
Yeah. It's compared from desired to achieved.
And then
the difference.
Because if the system, let's say that we have a system which is extremely clever. Okay. At the beginning, you have 180 degrees that you desire. Then you have 20 degrees, which is the room temperature because the oven is cold. Then you have here 120 degrees. Sorry, my mistake. 20 degrees. Here I have 160 degrees. And then it says, okay, I have to warm it up in order to achieve an increment of 160. And the system is so clever, say, okay, more or less it will be 400 watts. Put 400 watts and bob's your uncle. You get 180 degrees. Okay, so this would work. If you have a system which knows how much power you have to give to have a difference of temperature of 160 degrees, okay, but that's exactly what you do with the manual oven. You know that you have your knob there. You know that you want 180 degrees to bake your sponge cake. You put it there, and that's it. So it's set there. The problem is that if anything changes, it's not able to self-regulate.
What do you mean if anything changes?
Anything changes means, okay, let's say that suddenly the temperature drops in the environment.
Okay, like the door opens.
Like door opens or like boom, there is a storm and the temperature drops by 20 degrees. So boom. Okay. So the environment outside will be 0 now, not 20. And then
you mean like the reference changes?
No, the reference is you still want. This is what we call reference. Okay. So the reference is the set point, or
that's set points.
Set point. Sorry.
Yeah.
This is the set point. But then, so you say my set point is 160 80 degrees. The environment is 20, so I have to give an extra 160, okay? You give it there. But then the environment becomes 0. If you set as 160 the difference of temperature, like let's say that here I set 160. If in an open loop, I say 160 degrees gives me 400 watts, okay?
Okay.
So if I have the environment which is 20 degrees, I have 20 degrees plus 160, which is given by the oven. Inside the oven will be 20 plus 160, 180 degrees, okay? So inside my oven, outside I have 20 degrees, and inside I have 180 degrees. But then, if, see, yes?
No, I'm interrupting you.
So if the environment becomes 0,
then that becomes...
I still give 400 watts.
And it becomes 160.
160.
Okay, so we're assuming that the oven is not losing heat.
Yeah. Okay, no. Let's say that there is a constant thermal condition.
Because when I said reference, I didn't mean this. I meant this is the reference. Because when you're measuring it, you're going to have like, I might be jumping way too far ahead, your reference temperature, and that's going to be the temperature you use to see your change.
Okay, maybe we had different terminology.
Yeah, because how would this value here affect this? Where is it?
Oh yeah, typically it's here. Typically it's here.
Okay, there.
You can have some disturbance, so you can say, okay, this is what you give here, but then there is some external cause which changes the temperature that you achieve, okay? So you should always consider the 120 that you give plus some external causes. So if you put here some external cause which changes the temperature of the oven, like you open the oven or the environment changes, then this temperature will change. And if you give still the same power, because you set 400 watts constant, then you would have a different temperature. But if you have feedback, you say, okay, look, now here I have a disturbance. I subtract some heat. So the temperature, instead of being, let's say that we are in equilibrium, okay?
Okay, so we add 180.
We have 180, okay? And then here, of course, we have 180
okay,
degrees.
But the disturbance is 0.
And here you have 0 difference. The disturbance is 0, and we are all fine. But now the disturbance changes, becomes, for instance, negative. So it takes out some value. So the temperature drops to, I don't know, 160 degrees. Okay. For instance, you open the door or whatever.
Okay, so we got 20 at the top now.
Then
minus 20, excuse me.
Minus 20. Okay. Then what happens? Here I don't have 180 anymore, but 160. So here I have 20. And then say, okay, so 400 now with this disturbance is not enough anymore. So I have to give, I don't know,
450.
450, okay? Then I give 450, this becomes back 180.
But now it stays at 450.
Then here I have 180, this is 0. And then, fine, now I have 450 watts, it's enough with this disturbance. I remove the disturbance, for instance, I close the door of the oven, now this becomes 0. Now this will become larger because I have more power but no disturbance. So it will be 200 degrees. Now here I have 200 degrees, but then what I have here? Minus 20. It means that the temperature is larger than what we want because we have 200 degrees instead of 180. So they say, okay, the power now is too large. And
back to 400.
It drops, it decreases the power back to 400. And then again you have 100 degrees and bob's your uncle, okay? So this system is self-regulating. So it's able to read what you achieve and change it back, okay?
Yeah.
So every time it reads the output, and it will adjust the power it gives to the oven in order to have the correct temperature that you want. So, for instance, if we want to put it in a graph, like the very first example we did, was this. We said, okay, this is the time. This is the temperature of the set point, which is 180 degrees. And our oven is at 20 degrees. So the temperature of inside the oven is at 20 degrees. Then it reads that there is a difference of 160. And so we can draw here the power, okay? And we say it 0 watt at the beginning. So it will increase the power to 100 watts, okay? So this is 100 watts. The temperature will increase. It feels that there is still a difference, so it will increase the power to 200 watts, and the temperature will increase. Then it will increase the power to 300 watts. The temperature increase, and then finally you arrive to 400 watts, and the temperature will be 180 degrees inside, okay? So this is the point. At every loop of the circle of the feedback, it will read the difference. So it will read let me use this red chart.
Yes.
T set minus T inside. So it will take this difference and it will increase the power until this difference will become 0. Okay. Then if there is some disturbance, the temperature will drop, for instance, because you open the door. Here, it will increase to, we said, 450 in order to compensate the drop and so on. Okay? Fine. So why did I explain all these things? Is it clear how the feedback is? Okay.
Yeah.
Because the operation amplifier, in fact, does exactly this thing. Okay? The operation amplifier is nothing else than a device which, if you use it in feedback, performs these tasks.
Has an input, has output.
As input, as output, and what it does is to check at the input if this difference is 0. If it's not, it will adjust the output until it gets to 0. Let's make an example.
All right. So
everybody starts with the inverting amplifier, but then I realized it's better to start with the non-inverting amplifier.
All right.
Because I think it's easier to see the working principle of the feedback in the operation amplifier with the non-inverting amplifier. Do you remember how it's non-inverting? A non-inverting amplifier.
Oh,
so
okay. So we have the amp.
The amp,
and then
okay.
we have the negative and the positive.
Okay,
yeah.
no, you have
yeah.
the chart.
Okay.
Are you totally sure? a minor mistake.
Yeah.
This connection here is here.
Oh, pardon me. Pardon me.
Okay. So I will just redraw it if you don't mind.
Yeah, that's horrible. Yeah, please.
Okay. Now you will understand why it was that connection like that, okay? So we have our operation amplifier. So we connect our input voltage. So this is the ground. We connect it to the positive
input.
Then we connect like all the ground here. We connect a resistor, input resistor here, and then
a feedback resistor.
The feedback resistor, okay? And just, minus here. Yes. Just to use simple numbers, let's say that the input resistance and the feedback resistors are both 1 kilo ohm. Okay, simple. Nothing special. So 1 kilo ohm here, 1 kilo ohm here. And let's say that the input voltage is 1 volt. So, how does this system work? This system, the operation amplifier, is like that system with the oven. It will read this voltage here at the input. So the difference between the voltage at the negative, between the negative and the positive, okay? Then it will adjust the output voltage so that this voltage will be negative, okay? Will be zero.
Yeah.
Okay.
Yeah.
So let's say, for instance, that we start with an operation amplifier. I will just erase maybe this because we don't need it anymore. I need some space to explain what you are doing. Okay. So let's say that the output voltage is 0 volts, okay? And the input voltage will be 1 volt. Now we have to find the voltage at this point, okay? Let's call it V minus. So the voltage of the negative input with respect of the ground, okay? Let's call it V minus. Now, one thing we should know is the current here
is 0.
0.
And there.
And also 0, okay? So if you watch this circuit, and here also the current is 0. Now, it's 0 because there is nothing attached. If you connect,
if there's a load, yes.
It's a load, yes. But at this stage, there is no load. So we can say, okay,
yes.
The current here is 0, okay? Otherwise, no, because people typically, I don't know why, but a large percentage of my students, I always say, this current is 0, this current is 0, and then they think, also the current exiting the operation amplifier is 0. No. If you have some voltage here and you put some load, of course there will be some current.
Of course, yes.
But in this case, there is no load, so it's 0, okay? So,
well, besides the feedback load, right? Because some current will go through RF.
Oh, of course, there will be some current here.
Yeah.
Definitely.
Yeah. Yeah. Sorry.
I'm saying this current, okay?
Yeah.
So, as a matter of fact, here I have my amplifier, like this, which has the feedback resistor. It has an input resistor. Then, there is a connection here, which goes, but the current here is 0.
Yes.
Okay? And the current here also is 0. So we can consider it, this voltage, as the output voltage of the amplifier applied to 2 resistances in series, okay?
Yeah.
Fair enough?
Yeah.
So, and this is what?
A
This
voltage
is
divider.
voltage divider. This is
I'll call that VI. But yeah, V minus is okay.
okay, we can call it VI, but it's the same voltage that you have on the
it's
line.
at the same node.
And V input is in fact
0. Oh no, V in. Sorry,
this is also
V plus.
V plus,
yes,
okay?
Yes.
Because it's applied to the
positive input.
To the positive input. Okay? So V minus is, in this case, with these two resistors, which are the same, because we say that RF is equal to R input, and it's 1 kilo ohm.
Okay, yes.
So it's half of the output voltage, right?
Yeah. So we could say, maybe I'm jumping, V out is equal to V in multiplied by RF over RI, which is 1. So therefore, V out is equal to V in.
Yeah, you're jumping.
Sorry.
I just want to understand why we arrive to
that
to the final gain and so on. But especially I want to explain how the system works, okay? So this is V out divided by 2, because we have these two resistances. So in this case, the output is 0, so you have 0 divided by 2 is 0 volt, okay? So now let's calculate.
Just a note, it's divided by 2 because RF and RI are equal.
Yes, otherwise it would be
and
different.
The voltage divider rule says that would be half.
So VD will be what?
VD would be V in minus V minus.
So we have V plus minus V minus, which is V plus is V in, so it's the input voltage. I wrote input.
So 1 minus 0.
1 minus 0, which is
1.
1, okay? Okay, so let's say that now the difference between these two voltages is 1 volt, okay? 1 volt, so let's say that, now again, I'm giving random numbers just to explain the principle, okay? So I'm not very precise in what I'm doing here.
Yeah.
Just keep in mind this is the principle. So let's say that now, so that was the first step. I say, okay, now I'm feeling here that there is a difference of voltage. So I have to do something to reduce this difference of voltage. The same thing that we did with the oven, where the oven was feeling, okay, I want 180 degrees, I have 20 degrees, I have to do something to warm up the oven and therefore increase the temperature. Okay?
We have to do something such that the delta is 0.
Exactly.
Yes.
So I have to increase this voltage. It doesn't know how much. So let's say that V out now will be 0.4 volts. So here, my V out now is not 0 anymore, but it's 0.4 volts. Okay? V in is still 1 volt. V minus is what now? 0.4 divided by 2. Okay, so V minus, lost?
Wait, okay, so it raises the value to 0.4 because there's a difference in the inputs.
It says, okay.
Oh yeah, and now it's divided by 2 because it goes past the voltage divider.
Okay, so a voltage divider, if I have 0.4 volts between the output and the ground, again, I have the voltage divider, so here I get half of that. Okay?
Yes.
So I get V minus, it's 0.2 volts. Now let's calculate the difference. The difference is V plus 1 volt is always the same. At the input, at the positive input, we have 1 volt.
Yeah, so it's 1 minus 0.2.
Exactly.
So 0.8.
0.8. Now, good. We are warming up the oven. But it's not enough because the difference is still not 0.
So we push it more.
They say, okay, 0.4 is fine, but not enough. Let's go for 0.6 volts. What do I, 0.8, okay.
Okay, 0.8.
0.8, positive input
1 volt.
1 volt. Here I get 0.4. The difference now between these 2 points is 0.6 volts, right?
Yeah.
Because again, we have 0.8 volts at the output. It's divided by 2. So I get here half of the voltage, which is 0.4. So at the positive input, I have 1 volt. 1 volt. At the negative input, now I have 0.4. The difference, 0.6. Good, we are getting closer to 0, but not yet. So let's say that we get 1.2 volts at the output. Now, 1 volt, the negative input has 0.6 volts, and now the difference is 0.4, almost there. The amplifier is feeling that it's going well, so it gives more power to the oven, so it gives more voltage at the output. So let's say that we get 1.6 volts, okay? 1 volt at the negative input, at the positive input. Now 0.8 volt at the negative input.
0.2 at the difference.
0.2 at the difference until the last step. It says, okay, I put 2 volts there, and therefore I have 1 volt. 1 volt at 0. Bingo, it stops. Okay. So this is how the... Are you okay?
No, carry on, please.
So so this is how the operation amplifier works. It will feel how large is the voltage here. If it's 0, it doesn't do anything. If it's positive in this case, it will increase the output voltage until it will feel that the voltage is 0. Okay? If, on the contrary, I apply here minus negative 1 volt, it does the opposite. It does decrease the voltage until it will get to minus 2 volts, and then, again, I have 0 voltage here. Mm-hmm. This is the reason why you have to pay attention to the input of the operation amplifier. Because the operation amplifier only feels this input voltage, and it does increase or decrease the output according to the direction of the voltage. If now, in this example, it feels that the difference is positive, it means that it has to increase the output in order to have here the same voltage and have 0 input voltage. Mm-hmm. If you have negative difference of voltage, okay, it will decrease the output in order to get, again, 0 volts here. If you flip this input,
the opposite will happen.
If you put the negative here and the positive here, what happens? I apply 1 volt here. I have 0 if we start from the beginning, okay?
Okay.
0. And then it feels not the difference of 1 volt, but it feels minus 1 volt, okay? So it says, instead of giving 0.2, 0.4, it will give negative 0.4, okay? Let's make this example so that...
Yeah.
So let's say that we start from here, okay? Now, VD now is opposite, okay? Because we flipped the inputs. Now we have the negative here and the positive here. So you applied 0 volts. The positive input now has 0 volts, okay? Because now we reversed
the polarity.
The polarity, okay? So V negative will be 1 volt.
Yes.
And therefore the difference will be negative 1, okay?
Yes.
Negative, it means that I have to give what? Negative output voltage. So I decrease the output. But if I decrease the output, what happens? I have 0.4 volts, negative 0.4 volts here. Here,
negative 0.2.
Negative 0.2, okay?
The input is still...
But this is not V minus anymore. This is V plus. Because now this is connected to the plus, not to the minus. And here I still have 1 volt, okay? correct?
Yes.
So now the input voltage, I should probably flip this terminology. This is V plus, and this is V minus, because it's connected to the minus, okay? Are you okay? So now I should probably change also the color here. This is the V minus. Now, no. Now, V input is connected to the negative, okay? So this is V negative, okay? The positive is V out divided by 2, okay? So this is the positive, okay? Now, what I'm doing is to take 1, not minus 0 anymore, okay? So I take V plus minus V minus. But now V plus is V out divided by 2, because we connect it here, right? So now, V plus, okay.
Hang on, maybe I'm a bit lost. Okay, so the V input is 1. So we're putting 1 volt to the negative input. Therefore, the op amp is seeing negative 1 volts.
Sorry?
We're putting 1 volt in
yes.
the negative input.
To the negative input.
So it sees negative 1
So
volt.
here, the negative input now will be, if I have input negative, now this is the negative input as 1 volt. Okay. Now, the output, this is output voltage. Let's start from the beginning, okay?
Yes. Okay. So we have 0 volts.
0 volts. And now we have 0 minus 1, okay? Because we have V plus is 0.
Yes.
Because V plus is the output voltage divided by 2, okay? It's 0. Minus
1.
1, because the negative input is connected to the input. So we have 1 volt.
So now we have negative 1 on the output.
Volt, okay. Now, the amplifier feels that the input voltage is negative. So what we should do, decrease the output, okay? So now the output, instead of 0 volts, will be negative 0.4, because it's feeling a negative voltage. So it has to decrease it, okay? So
the
now,
input's still 1.
V minus is still 1 volt. V plus, instead of 0,
it's going to be negative 0.2.
0.2 volts. And now the difference between them,
it's going to be negative 0.8. Sorry, let me just see. So it's going to be 1 minus negative, so it's going to be 1.2.
It's going to be, it's V plus.
So it's negative 0.2 minus 1.
Minus 1 is negative 1.2.
Aha.
Correct?
Yes.
Then it says, okay, negative 0.8 volts. But then the output will, the difference between them will be, so the V plus will be negative 0.4, and the difference between them will be
negative 1.4.
Negative 1.4, okay? As you see now, the difference between the inputs is not decreasing as it did before, but it's increasing. And it's never gonna arrive to an equilibrium, because the more it feels a negative input, the more it will decrease the output. But if it does so, the more the difference between the two inputs will increase instead of converging to 0, okay?
It will saturate.
At some point, it will arrive to the output voltage, which becomes the maximum voltage of the amplifier, and then there it is, okay? So.
Okay, yeah, so the reason, pardon me, I said earlier that the relationship would be negative. It wouldn't be negative because the feedback is not on the negative side.
Exactly.
So the negative side,
the feedback should be always on the negative side.
Yeah.
So that's the reason why
we like negative feedback.
We like negative feedback.
Yeah.
Like, you know, that's always what they say, that the feedback is like a COVID test. You always like it to have it negative. You know, people say negative feedback. That's what always I say when I talk to people. and I say, yeah, I gave negative feedback. I say, oh, that's bad. No, it's good, negative feedback. And they get confused. No, I want positive feedback from my customer. No, I want negative feedback from the customers. These two inputs are not called negative and positive by accident. They are called negative and positive because we want negative feedback, which is what we were doing before. Before, you were taking 180 degrees, and you were subtracting the temperature from inside the oven. So then you got, I don't know, 20 degrees from inside the oven. Here you have 160 of difference, and therefore it means that if this is positive, you have to increase the temperature. And you call it negative feedback because here there's a negative. If you sum, you get exactly to this problem.
Yes,
okay?
It won't converge.
It will not converge. In order to converge, you have to subtract your reading from the set point in order to get 0 if they are the same.
Yes.
Okay? And so that's why when you have an operation amplifier, always the feedback, what goes from the output to the input, should be connected to the negative. Okay?
Yes.
Otherwise, the system doesn't work because
it's unstable.
It goes to the opposite. Okay? It will never get to this.
Pardon me, unstable is not the right word.
It's
unstable is like for oscillations.
But anyhow.
But we got to
the point.
Yeah,
okay.
Yeah, for sure.
So the operation amplifier is not so smart in terms of that it knows what the output needs.
It just has one rule. It's like get the difference to 0.
Exactly. Get the difference to 0. And in order to do so, it has to change the voltage. How does it change the voltage? It only knows in which direction to change it. Okay? So the direction is something that say, okay, I feel the difference of voltage with this polarity, I have to increase. I feel the difference of voltage with the opposite polarity, I have to decrease. Okay? That's the only thing it does do. It doesn't know how much it has to do, but it does so. It does increase or decrease the output until here gets 0. When it's 0, it's happy. Okay. Why I wanted to make this example? Because the rules are that.
Oh, for an ideal op amp.
So we have the current here 0. The current here 0, and again it's not true, but and then the voltage here at 0.
Yes.
And then people say, okay, but if the voltage here is 0, also this voltage is 0, correct?
Yep.
Why not? So what is the difference with flipping the polarity of the voltage, of the inputs? I mean,
nothing really.
If you have,
because the difference comes when the feedback is swapped.
If this is 0, okay.
Okay.
And this is 0, okay. It's the same. I don't see any significant difference between these two situations. Simply, the voltage between the voltage at this terminal and at this terminal is the same.
Yes.
So that's probably why students are often misled, and they think that these two terminals are irrelevant. You can put plus and minus wherever you want because the voltage between them is 0.
Maybe that's sort of true, but the key point is the feedback should be.
The point is that this is just the ending point of the feedback loop.
Yeah. The feedback is where the importance is.
The point is that.
Not importance.
Yeah, well, it tries with some feedback to go back to 0. The point is that, let's say, if you have, let's take the example before, okay? Time. You have, let's see, the input. Okay, let's draw again the schematic just to. Okay. So this is the input.
Okay.
And this is the output.
In a non-inverting configuration.
Non-inverting configuration. And the input, we said, is 1 volt.
Yes.
At the beginning, the V output, so let's say this is the output, is 0.
So it will slowly climb.
Then it will slowly climb, 0.2, 0.4, until it gets to 2 volts, okay? 2 volts here. It means that you have 1 volt here. And it means that V minus, this is...
Sorry, sir.
Mistake?
No mistake, but I'm confused. If RF and
they're the same, okay?
Yeah, why would it be 2 volts? I thought
because 2 volts. I have 1 kilo ohm here.
Now I understand that from the voltage divider perspective. Oh no. Inverting
inverting is
a non-inverting op-amp has +1 in the equation.
Plus exactly.
Yeah,
then
sorry.
Okay.
I jumped ahead and I confused myself. Yeah.
So then this is V out.
Yes.
V minus, remember, is V out divided by 2.
Yes, because the resistors are equal.
So it means that it will be V out would be divided by 2, okay?
Yeah.
So if you want to, let's see if the yellow can be red. Oh, yes, but maybe orange is better. Orange is the new VD. So, so this is VD. So maybe I will plot it here. VD at the beginning is 1 because we have 0 output. So VD is
yes.
0 output, 0 yes. V minus. So it's 1 volt minus 0. And then as V, this is also...
It will climb in the same manner as V minus.
It will drop, not climb.
It will drop?
Yeah, because that's from...
Oh, because they minus.
Yeah, they subtract. So if I take VD...
Oh, of course, yeah, it needs to go to 0. Oh my God, yeah.
Is V plus, which is always 1, minus V minus, okay? So this drops down until it gets to 0. Well, it's not
it will follow this one.
Yeah, it will go down here,
yeah,
okay?
Yeah, there you go.
Something like that, okay? So, this is how the operation amplifier works, okay? So then, if you are here, fine. VD is 0. You're happy about that, okay? But in order to have to 0, it will start from a point where it's not 0, and then gives the signal, gives the indication to the amp how to change V out in order to go back to 0. Okay?
Yes.
This is important because it tells you that it's not always 0. When we calculate the circuits, we use the rule of saying, okay, the difference between the inputs is 0. Hey, it's 0 if we are here. If we arrived to stability to the stable point, okay?
Okay, yeah.
But there is some transients.
Okay, wait, okay, yeah, please carry on.
Like if you change the input voltage, like you're here, you're fine, and you change your input voltage to 1.5 volts, then you will have another 0.5 volts difference, because now you have 2 volts at the output, 1 volt here, but now 1.5, so you have 0.5 volts. So again, it will increase.
And it will drop down again.
To 3 volts.
And V minus will climb to?
V minus will climb to 1.5, and the difference will drop down, okay? So it's true that when you are here at the end of the transient, VD is equal to 0.
Yes.
But before you arrive to the transient, this is not.
Oh, yeah.
Okay, so no, because sometimes
but a transient is.
It's not this is different because when you say the current here is 0, it's really 0 always. Okay, it's not true, it's 0.
Yeah,
It's
there's some input current.
Whatever. So, but this is always like that. VD is not always 0. It's 0 only if you are in equilibrium point. But before that, it's not 0 because it does need not to be 0 in order to give the signal to the op-amp how to change the output.
But that current goes this way.
Which current?
The current when this is not 0, when the difference is not 0,
the
current is not going that way.
No, the current here is still 0.
Yeah, that's why I mean the current is going down.
Which current? There is a current going out of here.
Yeah, coming in here, going down there.
Yeah, this is always like, it does always work. That, by the way, this is also irrelevant because we have the voltage imposed here. If there is an ideal voltage source here, before I was mentioned, okay, here the current is 0.
Yeah.
It is not really important because...
Yeah, we're talking about the feedback loop.
Yeah. Nevertheless, so the point is that always VD, when you change the output and you get like from 1, you go to 1.5, then it feels that now it's not an equilibrium anymore. This is like when you open or close the oven.
Yeah, exactly. Yeah.
So then you open, so it means that you give more power. So then you have to change it again. Okay.
Yeah, you affected the system, and the system needs to adjust itself.
It does adjust itself in order to get again to VD 0. Okay. So that's what the operational amplifier does. It's a sort of stupid machine. It does know only what to do, in which direction to increase or decrease the voltage.
Yes.
And then it does so until it feels that at the input there is not 0.
Tries its best.
Why did I want to explain this thing? The first reason is that at least you know how the operational amplifier works from the operative point of view, okay? I don't want to give just the rule like that, because otherwise you don't understand the rule, the VDU is equal to 0.
Oh, yeah.
Because otherwise you don't understand what...
Yeah, we need to take baby steps to get to the...
Exactly. So now we know how the machine works.
To understand
why
it actually does.
I will just try to propose this thing, okay?
Okay.
So keep in mind this figure, okay? So let's say that again.
Okay, let's go.
Here there is time. Let's say that you put 10 millivolts as
your input.
Okay.
All right.
And in that configuration, so again, let us draw negative plus.
Can I draw it?
Sure.
Yeah.
Enjoy. Oh, you have chalk. Perfect. So,
and yeah, ground.
So this is V out. Okay.
Yes.
So this is V input. This is V input. We might derive now the formula for the output. Okay. So this means that the current.
Okay. So KCL.
The current here is V input.
Oh, yeah.
Let's say that we are at equilibrium already, okay? So we have all our transient, we arrive to equilibrium, so the voltage VD is really 0, okay? This voltage here is 0. So it means that if this is no difference of voltage, V input
node A and VA equals 0.
No.
Because we're in equilibrium. First of all, we're in equilibrium.
With the respect of no.
No. Fine.
No. Be careful. With respect of the ground, no.
No, it will be V in.
V in. Yeah. So is V. Here we have V minus. So this is...
Oh, Vin minus Va equals 0.
Or, so if you call this...
Yes, excuse me. Yes.
And this is...
B.
V is Va minus VB, it's 0, okay? So it's V plus minus V minus, okay? So this current here in this resistor
That's
is...
II.
How do you calculate it?
Can I have the red one?
What?
Okay.
All right. Okay, so yes, let's call this I, okay? So the current in this resistor is equal to the current here because here the current is 0.
Yeah, so that's, we can do plus 0, just, just to keep it.
Just to be fancy and have everything polite, but, so these two currents are equal because here there is no current. So if the current arrives here and cannot go here, it means that it must go.
It has to go there, yeah.
Doesn't disappear.
So now we
but how do you calculate this current?
Oh, okay, so I is going to be VB minus 0. So it's going to be VB minus 0 over RI.
In this case, you know that the voltage here is already the input voltage, okay? Because you have the input voltage here, but then there is no difference between these 2 points. So the voltage here is equal to the voltage here, and that's the same voltage on the resistor.
Yeah.
So in fact, here you can write...
Say it's Vin.
Vin, okay?
Yes.
Fine.
IF?
IF is the same, okay? So V output...
IF is equal to V out minus VB, which is Vin.
Too complicated.
Oh, no?
Yeah, I know where you were going, but it's too complicated. V out, it's simply the voltage on the resistance RF plus the voltage on the resistance RI. Okay?
Okay.
So we can say voltage on RF, let's call it how? It's the voltage on the resistance RF. So
yeah,
you can say RF times IF, correct?
Okay.
Because the voltage on the resistance RF is IF, the current on IF, times RF.
Yeah.
Plus the voltage on RI, okay? Because
which is Vin.
Which is Vin. So, what is that?
It's VIR.
And what is it?
Oh, it's just to show that a voltage is I times R.
Ah,
which you did, yeah.
Okay. It's a mnemonic way to remember Ohm's law.
Yeah.
Ah, okay.
But you can remember many equations like that because it's always in a triangular form.
Okay. But this IF is equal to II, correct?
Yeah, yes, it is.
So plug, right, RF plus RF times II plus V in, okay? Equal, now instead of II, you have IN divided by RF times V input divided by RI plus V input, okay? Okay, and therefore you get input, yes, RF divided by RI plus 1, and Bob's your uncle.
Yeah.
Let's see if we can read it. Yes, on the screen we can read it. Okay. So this is the reason why if you have two equal resistors, 1 kilo, it gets 1 kilo divided by 1 kilo is 1, plus 1, 2. That's why if you apply, for instance, 10 millivolts, the output will be...
Times 2.
Times 2, so it will be...
If RF and RI are equal.
Yes, so if we have RF equal RI, then the gain will be 2, okay?
Yeah.
So you apply 10 millivolts at the input, and then let's use the blue.
So this is the gain, not
this. This is the gain. The gain is the output divided by the input.
Huh, okay.
The gain is how much it amplifies.
Oh yeah, I understand that. Yeah, I understand that.
If you take V out divided by V in, it means how big is V out with respect compared to the input voltage, and that's its ratio. So it's
the multiplier.
Okay. So let's say this is V out, okay, but it doesn't go directly to 20 millivolts.
Yeah, there's no step.
It has to boom, 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 rotate until it gets to 20 millivolts, okay?
Yes.
Fair enough. So it has some transient because it has not infinite speed.
Yeah, there's capacitances and inductances and
all sort of. We don't want to go inside on whatever.
Yeah.
We just know that in order that when it feels an input voltage, a difference of voltage between these two inputs,
it's not an instantaneous.
It has a transient until it arrives to have a zero here between the two inputs. Okay.
And just to diverge a bit on digress, if this was a computer, the analogy of this transient would be the loop speed it takes to go from one iteration to the second iteration.
Yeah, you can see that way. It's a little bit risky because it's not discrete. In a computer, if you have a for loop and it makes this computation, it has steps, like discrete steps.
Yes.
Like every iteration takes, I don't know, 1 millisecond, and then you arrive. In this case, it's not.
It's continuous.
It's continuous. So, but you understand the principle, okay?
Yeah.
So this is VD, okay. Now, the speed is defined by how fast the output can change.
Okay.
So this is V out. Okay. V out.
Oh my God, I'm in the way as always. Okay.
So V out has a finite speed it can change. So in fact, if you watch the data sheet of any operation amplifier, you will find a value which is called slew rate.
The slew rate.
Slew rate tells you how fast the voltage can change. Now, ideally, it would be infinite because you apply 10 milli, gain it is 2, you get 20 milli. So ideally, it should be like tack, tack.
But nothing in life is like that.
Yeah, so it has some finite speed.
Yes.
The voltage can change. So the slew rate is this slope here. So you can take this slope. It tells you how many volts per microsecond it can change. I don't know. If I tell you that the slew rate is, I don't know, 200,000 volts per second, or typically it's given in volts per micro, okay?
Yeah.
But how many volts per microsecond you get, something like that. So it tells you that the slope is the volts per second.
Change per time.
Exactly. So the larger is the slew rate, the larger is the slope, because it means that in the same second, it rises more. Okay.
Yeah.
So this is typically it's given in volts per microsecond, but now let's go back to our example. So let's say now let's draw only V out. Okay. In this case, it was going to 20 millivolts because the gain was 2, and the speed of the output change is limited by
the slew rate.
The slew rate, okay? Now, what if the input becomes, I don't know, 100 millivolts, okay? 100 millivolts means that the output now will be 200 millivolts. So instead of arriving to 20 millivolts, now the output of the amplifier will be
200.
200.
But it might not follow the same.
It will behave like this, okay?
Okay.
Because the slew rate is still there. You cannot make it go faster. That's the limit. It can change.
Yes, yes.
But in order to arrive to 200 millivolts, because now we arrive here, it takes more time, okay? So if you have a larger gain, the output of the
amp?
Of the op-amp will take longer time to arrive.
Oh, so higher gain, slower response.
Ding, 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 ding. We will arrive to that at the end. Okay. Now keep it in mind, this figure. Okay. We say it. Now I will draw only the output voltage. Okay. So now we say that we apply 10 millivolts here.
Yes.
Okay. So we have 10 millivolts here, and the gain is 2. Okay. So it means that the output voltage will be 20 millivolts, okay? So it means that our voltage will start and arrive at 20 millivolts, correct? Now, let's say that at the input we still have 10 millivolts, but we change the gain. The gain becomes 10.
Okay.
How do you get a gain of 10? Remember that here you have feedback resistor divided input resistor plus 1. So if you choose, for instance, a feedback resistor of 9 kilo ohms, the input resistance of 1 kilo ohm, you get 9 plus divided 1 is 9 plus 1, you get a gain of 10, okay?
Yes.
So in the input you still have 10 millivolts, but now the gain is not 2. Now the gain is 10. So the output voltage will be
100.
100 millivolts, okay? So now we don't arrive to 20, but we arrive to 100 millivolts, okay? Which means that the output voltage, okay, I forgot to write here that this is the output voltage, still rises, still is increasing with the same slew rate, because that's the speed of the amplifier. You cannot do anything else. That's the limit of how fast the output voltage here
can change,
okay? So the slope here is the same. But you have to arrive to 100. You have to climb up to 100 millivolts. So it means that it takes longer. Here, after some time, I'm already at my goal. Here, in order to arrive to 100, I take longer time, okay? So as you see, for a given input, the input is the same, okay? But you have a different gain. If you change the gain, if you increase the gain, then it takes longer time to arrive to the equilibrium point, okay? And this is important because it tells you how large can be your gain according to the speed of the signal that you want to do, okay? So for instance, let's say that you have a square wave, okay? Let's say that you have a square wave and you want to amplify it.
Oh, it'll become a triangular wave.
Exactly.
Yes.
You have, this is the input voltage, okay? And it's 10 millivolts, okay? 10 millivolts amplitude. The output with a gain of 2 will be, as we saw, something like this. Okay? So it's not perfect, but fair enough, okay? So here we have an amplitude of 20 millivolts, okay? It's amplified by a gain of 2. What happens if you squeeze the frequency, okay? So what happens if you make this signal faster, okay?
The slew rate will become more apparent.
Let's say that, or better, what happens if you, first let's make this example. If you increase the gain to 10, okay? Now, it will, so not 0,
yeah.
10, it will go to 100 millivolts. So let's say that this is going to be our 100
okay, so
millivolts.
we're swinging in the negative rails.
Wait a second. So the gain is 10. We go to 100, so it will take longer, okay, to arrive to 100 millivolts. This is not to scale.
Yes,
okay?
yeah.
So it will arrive here.
It will drop.
It will drop to negative, and then it's going to that. Okay.
And now we've got a shark fin.
So actually here it will start from here, okay, from the negative minus 10, okay. Minus 100, okay. Because now it has to reach 100 millivolts instead of 20, so it will take longer to arrive to 100 millivolts with the same slew rate. Okay. Okay, so let's now take this figure and let's see what happens if we squeeze the frequency, if we increase the frequency. Okay.
Yes.
Still, we have 10 millivolts at the entrance, but it's going to be this fast. Okay.
Yeah.
So this is the input voltage, which is going to be 10 millivolts. If you have the output voltage with gain 2, it will be like this, like this, like this, like this, and so on, okay? Still, you can see that it has time to arrive to 20 millivolts.
Because the gain is low.
Because the gain is low. But if I want, now let's make it to scale, okay? Now, I want to arrive to 100 millivolts because this is the out with the gain of 10, okay? But it has the same slew rate. So good luck with that. It starts here, and when it's still increasing, it's already time to go down, okay?
Oh, so you're going to lose the signal?
Yes, because it does not have time. It would need this time to arrive to 100.
Yeah.
To arrive to 100 millivolts. But by the time this is increasing, by the time you try to, by the time it...
Yeah, you try to get to it, it's already changed.
It's already changed to go down. And then it goes down, it would need this time to go down, but again it's time to switch up and go up, okay?
Remember in census class you taught us that some multimeters have a frequency limit. Because let's say you measure, I don't know, a 200 volt sine wave at like 6,000 kilohertz.
It depends on the amplifier that they have inside.
Yeah, and that slew rate limits this.
That's a lot of things that can limit them, okay? But one of the, if inside you have operation amplifier which amplify the voltage that you take and so on, and the amplifier do not have infinite bandwidth. They are limited, okay?
So, but this is just, this is not the bandwidth, this is the slew rate.
Wait. This is, again, is the bandwidth.
So the slew rate and the bandwidth are sort
of... They are extremely connected, okay?
Yeah. Okay.
Now, this means that, for instance, here, more or less, you can say that you can still have a square wave, okay? So still, it has time to reach the steady state point.
Yes, it converges.
The convergence to the 20. So gain 2 10 millivolts input, 20 millivolts output. Of course, it's not infinite. It will never arrive there. But at least it will not arrive there in 0 time. Okay, you always have a transient. But at least it has time to arrive to 20 millivolts. Here, it does never arrive to 100, which means that for this frequency, for this input frequency, a gain of 2 still works. But a gain of 10 doesn't work anymore, which is important because it tells you that the bandwidth, which means the maximum frequency you can put in the input and to have a working output, because here you see it will never go to steady state. It means that VD is never going to be 0 because it never rises to 100 millivolts, okay? So in this case, this frequency is out of the bandwidth of the instrument, okay? Because you don't have time enough to go to steady state. So we have an input frequency, and for gain equal to 2 is fine. For gain equal to 10, no good. Which tells you that the bandwidth, so the maximum frequency you can use this instrument, is depending on the gain. Okay?
Well, yeah, okay. Well, it depends on the gain and the slew rate. Because if your slew rate is greater...
The slew rate is there. The slew rate is a parameter of the instrument, okay? For that given instrument, with that specific slew rate, with that specific capability of changing the output fast enough or not, then if you input a frequency, that frequency can be properly amplified depending on the gain. The lower is the gain, the larger is the frequency which can be amplified by the instrument, okay?
So the gain affects the frequency response?
Yes, yes, exactly. Okay. So if you increase the gain, then only a slow frequency will be able to be amplified. If you have a low gain, then also large frequency. So if you, in fact, now I wanted to do it later, but at this stage, now let's go through that, okay? Let's say that this is the frequency, and
the response.
This is the gain.
The gain, okay.
Okay, gain. And let's say that the gain is constant. Let's say that you choose a gain equal to 2, okay? It's constant until some frequency. So this means that the operation amplifier works properly. So we have our operation amplifier like that. We put 1 kilo here. We put 1 kilo ohm here. And this is the output. This is
the input.
The input. And your gain will be the output divided by the input, okay? In this case, 2, because we have RF equal to R1. This means that you put an input voltage, you get here double that input voltage, whatever is the frequency, okay? We put a sine wave, we put 1 Hertz, 2 Hertz, 10 Hertz, 100 Hertz, and so on. At some point, it's becoming too fast, okay? You put a frequency which changes too fast. So let's say now that you put a sine wave, okay? So this is your input, and it has some frequency, okay? Now, if this frequency requires here a rate of change which is larger than the rate of change of the output should now change with the same rate of the input. But the maximum slew rate is this one. So it doesn't, is not able to reach that level.
So therefore the gain will decrease with frequency.
Decreases with frequency, okay. At some point, it's not fast enough to follow the input.
And that's what, the cutoff frequency?
This is the cutoff frequency, okay? You define it where you get to minus 3 dB, okay?
Yeah, where
which
there's
is
attenuation.
0.707, okay? So when you see that this is dropping down, it means that the amplifier is not fast enough to change, in changing the output, to follow the input, okay? If it's slow, it will follow the input, okay? But if it's not fast enough, if the frequency is too large, the input has a change of a rate of change, a speed of change, too fast for the amplifier, so the output is not able to follow the input.
To keep up. Yes.
To keep up, exactly. I was trying to find that verb. I didn't manage to. Okay, but as I told you, this depends on the gain. Okay? So, again, I have the same input, but now I have a gain of 10.
Yeah, there it is, 10. The cutoff frequency will be earlier.
Exactly. So here I will already start going down because I have to reach a larger voltage. So I would need here higher speed of change for this, okay? If you have a gain of 2, you have this speed, okay? So you have this slope with a gain of 2. If you have a gain of 10, the voltage will be larger, so the slope will be larger, okay? So you arrive to the point where you cannot keep up before for a larger frequency.
Yeah.
You understand? So here, boom, I've already started going down because I need faster response to amplify faster, to amplify bigger, okay?
Yes.
And so on, So this is how the response looks like in an operation amplifier in a feedback loop. The larger is the gain that you want, the faster should go to keep up the input because it has to reach larger output voltage, but then it means that it will stop being able to keep up with the input before, because at the end of the day you still have the same maximum rate of change in the output, okay? What does it mean? It means that, let's say that this is 1. In the data sheet, they typically give you this point, okay? They tell you that with a gain of 1, you have, so I don't know, for instance, 1 megahertz, okay? Sorry. So you have something like that. They tell you, okay, if your gain is 1, so output equal to the input, the maximum the cutoff frequency is 1 megahertz, okay? Then they tell you that the product of the gain and the bandwidth is constant, okay? So they tell you that this is a straight line, and they tell you, okay, what if you want a gain of 10, okay? Where is the cutoff frequency for a gain of 10?
Bandwidth divided by gain.
So if you have gain equal to 1, the cutoff frequency
is 10 mega.
1 megahertz.
Okay, 1 mega.
For instance, gain 10, then the product must be the same. So it will be 0.1 megahertz, okay? If you want a huge gain of 100, then the product must be the same. So it's 0.01 megahertz, okay? So when you make your design, you're saying, okay, which is the maximum gain I want in my project? I don't know. You have to amplify your signal by 100 times, okay? Because, I don't know, whatever.
The sensor needs to see something.
The design of the project requires you to amplify 100 times. Okay, say, cool, 100 times. What does it mean? I have to take the cutoff frequency with the gain 1, which is a data that you get from the data sheet. And then, this is for the gain 1. If you have 101, you have to divide and you get...
Is the cutoff frequency always corresponding to gain of 1?
This is the data for the data sheet that you get.
Yeah.
The data sheet gives you the cutoff frequency for unity gain.
Okay.
So you have to find the value of the cutoff frequency for the unity gain. Okay. Once you have that value, then you can rebuild this curve, because you know for each gain which is the moment when it starts dropping down. Okay. And then you have, in this case, 10 kilohertz. Okay? Which means that you cannot buy an operation amplifier and say, okay, which is the bandwidth of that amplifier? It depends. It depends on the gain.
Okay, yeah. Gains are bandwidth is not constant.
The bandwidth depends on the gain that you want. So it's not always the same, right? It's not constant.
Huh.
So it depends. If you want to amplify a lot, then you have to consider that you can do it only with low frequency.
I had 100 megahertz, I don't know, frequency response on this op amp I used for my thesis, and the gain is 21 in a differential mode.
I have to check the data sheet. It's but
no, the frequency is 100 megahertz.
So the unity gain bandwidth is 100 megahertz.
I think so.
Wow.
That's fast, right?
Should be, yeah. Like if you take a...
Well, it wasn't a cheap amp.
OP07, the one that you use in the laboratory, they have 0.6 megahertz, yeah.
Okay, so that's like nothing.
It depends on what. If you want to amplify like static signals, it's fine.
Yeah, this is to measure currents in a motor.
Okay. Now, so this is what you do when you want to design a system. You have first to decide which is the gain, the maximum gain that you want to use, and it depends on the project that you have to do. Okay, and then you watch at the unity gain bandwidth, and then you know that the product is constant, and then you decide, okay, I want a gain of 100. I have to take the unity gain bandwidth and divide it by 100 to get it. Just to be clear, this is in logarithmic scale, okay? So this looks like a line.
But it's
because it's in logarithmic scale,
yeah,
so if you plot the gain and the frequency
in a linear region?
In a logarithmic scale, it's like that.
Yeah.
If you plot in logarithmic region, it's going to be like this, okay? So that's why the product is always the same. Okay, so bandwidth times gain is this area is equal to the bandwidth times gain here, okay? So the area under this is always constant. But you do it in logarithmic scale, that's why it typically looks. So this is in log scale, this is in log scale, so you have 1, 5, 10,
100,
100, and so on.
Yeah.
So then you have 1, 10, and so on, 100, and then it looks like this, okay?
Because when you plot an exponential in log, it becomes straight.
Okay, so this was about the basic of how an operational amplifier works.
Yes.
Now we can see different circuits. Now that we know how the operational amplifier works, we can watch different circuits and we can try to solve them to see like some exercises like that.
Okay.